Have you ever stopped and wondered how an AI actually makes a decision? I mean, it's not just about crunching a ton of numbers. Deep down, some of the most powerful AI uses a process that looks, well, it looks a lot like human reasoning. It builds an argument, step by logical step, to get to a conclusion. Today, we're going to pull back that curtain and see exactly how these machines think.
So here's our game plan. We'll kick things off with a look at the AI's brain, the part that actually does the heavy lifting. Then we'll get into two totally different ways it can think. We're going to do a deep dive on one of them. I like to call it the clue collector method, and then we'll glance at its opposite. After that, we'll see where all this stuff pops up in the real world, and we'll wrap up with what it all means for the future.
All right, first things first, let's get right to the heart of it all. What is that central piece of the puzzle that lets a rule-based AI think logically?
It's not some kind of black magic, but it is a beautifully designed system. The real thinking all happens inside this one key component that acts like the AI's central processor for all things logic.
So just like our brains process what we see and hear to draw conclusions, a rule-based AI has something called an inference engine. You should really think of it as the system's cognitive core. This is where the thinking actually happens. It's the engine that drives the whole logical process forward.
So here's the bottom line. The inference engine is what connects the dots. It takes a big library of facts and rules, the knowledge base, and it just systematically applies those rules to the facts to uncover or infer brand new information. It's basically a little logician living inside the machine.
So, how does this inference engine actually work? Well, it's not a one-trick pony. It has two main strategies for reasoning, and believe it or not, they're pretty much polar opposites.
Okay, to make this super easy to understand, let's picture two detectives on a case. On the left, you've got the clue collector. This detective shows up, starts with the evidence on the ground, and just follows the clues wherever they happen to lead. This is a totally data-driven approach. But on the right, we've got the hypothesis tester. This detective starts with a hunch, a suspect, and works backward, trying to find evidence that proves their theory right. That's a goal-driven approach.
So that clue collector's method, the official name for that is forward chaining. It's what we call a bottom-up approach. You start with what you know for sure, the raw data, and you build your way up rule by rule toward a conclusion.
In our hypothesis testers method, that's called backward chaining. This is a top-down strategy. You start with the thing you want to prove, the goal, and you work your way backward to see if the facts you have actually support it.
Okay, so let's really zoom in on this clue collector method. How does forward chaining actually work, step by step? We're about to see how an expert system can take a bunch of known facts, apply some simple if-then rules, and build a logical chain all the way to a final goal. The process itself is actually wonderfully simple. It's just a loop. First, you start with your initial facts. Then, the inference engine looks through all the rules to see if any of their conditions, the if part of the rule, are met by the facts it already has. If it finds a match, that rule fires, and the conclusion, the then part, gets added as a brand new fact. And then, the whole process just starts over with this new, bigger set of facts.
All right, let's see this thing in action with a classic example. We've got a bunch of statements and one very clear goal. We have to prove that this guy, Robert, is a criminal, using only the facts and rules we're given. So how would a forward-chaining system solve this?
First up, the system takes all those statements and just turns them into simple, known facts. We know Robert is an American. We know there's a missile called T-1. We know country A owns that missile. And we know that country A is an enemy of America. These are our starting clues, our facts on the ground.
Now the inference engine starts to connect those dots. It sees the fact, country A is an enemy, and applies a rule to create a new fact, country A is hostile. Then it looks at two more clues. Robert sold missiles to country A, and country A owns missile T-1. From that, it deduces another critical fact. Robert sold missile T-1 to country A.
And this is the final step, and it's brilliant. With all these facts now established, Robert is an American, he sold T-1 to country A, T-1 is a weapon, and country A is hostile, the main rule can finally fire. If an American sells a weapon to a hostile nation, then they are a criminal. All the conditions are met. So the conclusion, criminal, Robert, is added to our list of facts. The goal is reached, case closed.
So now that we've seen the clue collector do its thing, let's just take a quick peek at the hypothesis tester's method, backward chaining. Seeing this will really highlight just how different these two approaches are.
Let's use a way simpler example here. Imagine our goal is to prove that a pet named Fritz is green.
Instead of starting with what we know about Fritz, a backward chaining system starts at the end. It asks, okay, if Fritz is green, what would have to be true?
So check out how the logic works in reverse. The system starts with the goal: prove Fritz is green. It finds a rule that says if it's a frog, then it's green. So okay, the new goal is to prove Fritz is a frog. The system finds another rule: if it croaks and eats flies, then it's a frog. Now it just has to check its facts. Does Fritz croak? Yes. Does he eat flies? Yes. Bingo. Since both of those are true, Fritz must be a frog. And since he's a frog, he has to be green. It worked backward from the conclusion right to the evidence.
So these are two very different ways of thinking, but they're not just some abstract ideas in a computer science textbook. They're being used all around us, in systems we interact with every day. And this really matters, because the method you pick completely depends on the problem you're trying to solve.
This table really breaks it down perfectly. Forward chaining, our clue collector, is data-driven, bottom-up. It's awesome for things like planning or monitoring, where you have a ton of data coming in and you just need to see where it leads. Backward chaining, our hypothesis tester, is goal-driven, top-down, and it's perfect for things like diagnostics or debugging, where you have a specific problem you need to explain.
Think about a fire alarm. It's the perfect real-world example of forward chaining. It doesn't start by asking, is there a fire? No, it starts with the data. The sensors detect the fact of smoke or the fact of high heat. Those facts trigger a simple rule: if smoke, then sound alarm. It reasons forward from the data to the conclusion.
And for backward chaining, medical diagnosis is the classic example. A doctor might have a hypothesis. I think this patient might have diabetes. That's the goal. They then work backward, looking for evidence. Okay, I need to check their blood sugar. I need to ask about fatigue or thirst. They are starting from a specific goal and searching for the facts that prove or disprove it.
So, we've seen how these basic reasoning systems can turn a pile of facts and rules into logical conclusions. And that brings us to one final, really interesting thought about where all of this is going.
You know, we built these systems to copy a very specific, structured version of our own logic. But as they become exponentially more complex, handling millions of rules and facts in seconds, they might start finding logical paths that we've never even thought of. So the big question is, will these artificial minds eventually expand our own idea of what it even means to reason? Definitely something to think about. Thanks for tuning in.